Today, we will be discussing section 7.8, improper integrals. To start off, let's think of the function f of x equals 1 over x. What if we wanted to find the area from 1 to infinity? So graphically, what we're looking at is, what would this area be from 1 to infinity? Would that area be finite or would it be infinite? In other words, what if we were asked to evaluate this integral from 1 to infinity of 1 over x dx? Earlier in this book, we looked at definite integrals, where both limits of integration were finite values. In this section, we're going to learn how to deal with an integral that has an infinite limit of integration. In general, when we have an integral of this type, these are called type 1s. We're going to look at another type later on. So if we have an integral from a to infinity, for example, of f of x, we would change that into a limit from a to t, both of those being finite values. And then after we do the integration, we'll take the limit as t goes to infinity. So it would become the limit as t goes to infinity of the integral from a to t of f of x dx. If instead the infinite limit is negative infinity, the bottom limit, we would then change that to be the limit as t goes to negative infinity of the integral from t to b. So again, we integrate with two finite values, t and b, and then once we're done, we take the limit as t goes to negative infinity. If instead both of our limits of integration are infinite, we would then need to break this up into two integrals. The integral from negative infinity to c, where c is some value, any value between negative infinity to infinity of your function, plus the integral from c to infinity of your function. Let's take a look at this example. We have the integral from 2 to infinity of 1 over the quantity x minus 1 squared dx. We can see that our upper limit here is infinite. So what we would need to do is change this into the limit, and you can use whatever letter you want. I tend to use a, as a goes to infinity of the integral from 2 to a of 1 over x minus 1 squared dx. We could think of that as the limit as a goes to infinity of the integral from 2 to a of x minus 1 to the negative 2 power dx. At this point, you could either use u substitution, or knowing that your u would be x minus 1, we know the derivative of that would just be dx. So this is going to give us the limit as a goes to infinity of x minus 1 to the negative 1 power, and then divided by our times negative 1, evaluated from 2 to a. Let's go ahead and substitute in our limits of integration. We end up with negative 1 over a minus 1 minus a negative, so that would be positive, 1 over 2 minus 1. If you go ahead and let a go to infinity, this entire fraction here would go to 0, and we just end up with 1. So that was an example of an infinite integral, or an improper integral, an infinite area that ended up approaching a finite value. Let's take a look at this example. The integral from 2 to infinity of 1 over the quantity x minus 1 dx. We do notice that one of our limits is infinity here, so we would need to change this into a limit of a definite integral. So we have the limit as a goes to infinity of the integral from 2 to a of 1 over x minus 1 dx. At this point, we could write out our u substitution, but we're going to use our u as x minus 1 which means the du would just be dx. We would end up with the limit as a goes to infinity of ln of the quantity, the absolute value of x minus 1, evaluated from 2 to a. If we substitute in our limits of integration, we get the limit, as a goes to infinity of the quantity ln of the absolute value of a minus 1 minus ln of the absolute value of 2 minus 1. This becomes ln of 1, which is equal to 0. As we let a go to infinity here, this also goes to infinity. So we get infinity. In each case above, if the limit is finite, like it was in the first example, we say that the improper integral converges. If the limit does not exist, like the last one we just did, then we say that the improper integral diverges. Let's look at this next example. The integral from negative infinity to infinity of 1 divided by 1 plus x squared dx. You'll notice that both of our limits of integration here are infinite. So we are going to need to break this up into two integrals. We can split this at any value in between negative infinity to infinity. One spot that most people like to use is 0. So we would split this up into the integral from negative infinity to 0 of 1 divided by 1 plus x squared dx plus the integral from 0 to infinity of 1 divided by 1 plus x squared dx. This becomes the limit as, let's go ahead and use a for this first integral. A goes to negative infinity of the integral from a to 0 of 1 over 1 plus x squared dx. Plus, and we could change the second one, we'd have to try or use a different letter. So maybe b, the limit as b goes to positive infinity of the integral from 0 to b of 1 divided by 1 plus x squared dx. The integral of 1 over 1 plus x squared is going to give us arctangent. So this becomes the limit as a goes to negative infinity of arctan of x evaluated from a to 0 plus the limit as b goes to infinity of the same thing, arctan of x, but our limits are different here, from 0 to b. Let's go ahead and substitute in our limits of integration here. We get the limit as a goes to negative infinity of arctan of 0 minus arctan of a plus the limit as b goes to infinity of arctan of b minus arctan of a. Now we need to remember what the arctangent graph looks like in order to determine some of these limits. The arctangent graph has asymptotes up here at y equals pi over 2 and at y equals negative pi over 2. And it looks something like this. So as we look at these limits, arctan of 0 is equal to 0. What about as a goes to negative infinity? Arctan of a, if we look at our graph, as we're going to negative infinity, our function is approaching negative pi over 2. So this would be negative pi over 2. So I have 0 minus a negative pi over 2 there. Here, arctan of b, as b is going to infinity, again from the graph we can see that the graph of arctan as x goes to infinity goes to positive pi over 2 minus, and then, oh, you know what? That was supposed to be a 0. I'm sorry. Do you guys see my mistake there? This lower limit was 0, and I put a instead of 0. Okay, so arctan of 0, again, we know is 0. So if we look at the values we got here, we have 0 minus a negative pi over 2. That gives me pi over 2 plus pi over 2. So our result here is just going to be pi. Let's look at this problem here. The integral from 1 to infinity of the quantity 1 minus x times e to the x, or e to the negative x dx. Once again, we have one of our limits being infinity. So we would now need to change this into the limit as a goes to infinity of the integral from 1 to a of the quantity 1 minus x e to the negative x dx. There's a couple different ways that you could now integrate this problem. We could distribute the e to the negative x and use integration by parts on this section and not on that. Or we could go straight to integration by parts with this whole thing. I think I'm going to do that. In that case, I'm going to let my u be 1 minus x. My du then, or I'm sorry, my dv would then be e to the negative x. Let's organize our work here using the tabular method. If we take the derivatives here, the derivative of 1 minus x is negative 1, and the derivative of that is 0. The integral of e to the negative x would be negative e to the negative x, and we integrate again, we get e to the negative x. Now let's organize our work here. We have plus followed by minus. Okay, so this is going to give me the limit as a goes to infinity of 1 minus x times e to the negative x. Looks like then we have plus e to the negative x evaluated from 1 to a. This gives us the limit as a goes to infinity of, if we go ahead and substitute in, 1 minus a divided by e to the a plus 1 over e to the a minus, substituting in 1 minus 1 over e to the 1, and then minus, again, 1 over e to the 1. So if we go ahead and take that limit, in this first quantity here, we see that in the numerator we have a linear term, and in the denominator we have exponential. So we know as a goes to infinity that the exponential term will eventually overpower the linear, and this whole thing will go to 0. You could also apply L'Hopital's rule here to see that you would get 0 as the limit. So we get 0, and again in that second term, again as a goes to infinity there, this whole thing would go to 0. The third term is equal to 0, and the fourth term is 1 over e, or negative 1 over e. So if we add all those up or subtract here, I end up with negative 1 over e. We're now going to look at a different type of improper integral. Let's take a look at this problem here. We have the integral from 0 to 2 of 1 over x squared dx. Now in this problem, neither of our limits are infinity, but we know that this function is not defined at 0. It is a little bit harder to realize that an integral of this type is improper because it's not easy to see that one of the limits is infinity or negative infinity. So now we have to think a little bit harder when we're looking at an integral and determine if the function given is defined at every value between 0 and 2, including the endpoints. If we look at the graph over here, we see that what they're asking us to do is to find the area under the curve here between 0 and 2. So you can see that again, this area is going to go up to infinity there. So what we need to determine, again, is whether this area is going to approach a finite value or if it will continue to grow unbounded. This is the next type of improper integral that we're going to be looking at. In general, these types of improper integrals, which the book refers to as type 2, are defined like this. If you have a function f of x continuous on a, b, not at a, but it is continuous at b, and discontinuous at a, then the integral from a to b of f of x dx is equal to the limit as t approaches a from the right of the integral from t to b of f of x dx. So again, we've now made this the limit of a proper integral where our function is defined at all values between t and b. Okay, if f of x is continuous on closed interval a open at b and discontinuous at b, then we would just change the integral slightly. It would become the integral from the integral from a to b of f of x dx would become the limit as t goes to b from the left of the integral from a to t of f of x dx. Because we're going to be approaching b now, which it was our upper limit, from the left of b. A is to the left of b. So from a to t, then t is going to approach b from the left side. If f of x is discontinuous at c, which is somewhere in between a and b, and continuous everywhere from closed a to open c, and open c to closed b, then we would say that the integral from a to b of f of x dx is equal to, and we're going to have to split the integral up at c. So we'd say from a to c of f of x plus c to b. And then we would have to use the strategies in 1 and 2 here to do each of these integrals. The improper integral is called convergent if the corresponding limit exists, and divergent if the limit does not exist. Let's go ahead and try the first example like this. We have the integral from 0 to 1 of 1 over the cube root of x dx. Let's go ahead, well, where is that function undefined, at 0 or 1 or somewhere in between? This function is undefined at 0. So what we would now need to do is to rewrite this as the limit as a goes to 0 from the right of the integral from a to 1 of x to the negative 1/3 dx. This is going to give us the limit as a goes to 0 from the right of x to the 2/3 times 3/2 evaluated from a to 1. Let's go ahead and substitute in our limits of integration there. We get the limit as a goes to 0 from the right of 3/2 minus 3/2 a to the 2/3. Okay, this gives me 3/2, and then this fraction here, as we let a go to 0 from the right, this also goes to 0. So that would just give me 3/2. For this next integral, we're asked to take the integral from 0 to pi of the quantity tangent of x plus 1 quantity dx. If you remember, the graph of tangent has a discontinuity at pi over 2. So before we integrate this, we need to separate this into two separate integrals. The integral from 0 to pi over 2 of tan of x plus 1 plus the integral from pi over 2 to pi. Of the same quantity. Now, because we have a discontinuity at pi over 2, both of these will need to change into the limit of an integral. So let's look at the limit as a goes to pi over 2. And what direction will we be approaching pi over 2 from for that first integral? Since we're looking at the integral from 0 to pi over 2, and 0 is to the left of pi over 2, we'll be approaching pi over 2 from the left. For the second integral, we'll be looking at the limit. Let's use b here, approaches pi over 2. And again, for that second integral, we're looking at the integral from pi over 2 to pi. And since pi is to the right of pi over 2, we'll be going this way and approaching it from the right. Oops. Sorry, I meant to put b to pi. Of tan of x plus 1 dx. Sorry, I ran out of room there. This problem takes a lot of space, so I'm trying to save as much space as possible. Okay, well, we can go ahead and integrate tan of x using one of our basic integration formulas, which says the integral of tangent of x is equal to the natural log of secant of x. So this will now become the limit as a goes to pi over 2 from the left of the natural log of secant of x plus x, evaluated from 0 to a, plus the limit as b goes to pi over 2 from the right of the same thing, natural log of absolute value of secant of x plus x, but this is now evaluated from b to pi. I think I'll have enough room to write this down here. This becomes the limit as a goes to pi over 2 from the left of ln of secant of a, plus a minus ln of secant of 0 minus 0, plus the limit as b goes to pi over 2 from the right of ln, absolute value of secant of pi, plus pi, minus ln, absolute value of secant of b, minus b. Now, if you remember what the graph of secant looks like, I'm going to sketch it right here. We know secant is 1 over cosine. So cosine looks like this. So secant would have an asymptote here. And if you remember, it looks something like this. This is pi over 2 right here. Okay, so as a is approaching pi over 2 from the left, secant of a is approaching infinity. So this here is going to infinity. So ln of something that's getting larger, this whole thing there, is also going to infinity. A is going to pi over 2, and secant of 0 is 1, ln of 1 is 0. So this is equal to 0. So what that means is that this first integral here, the limit as a goes to negative pi over 2 of all that, that diverges. That goes to infinity. If you look at the note underneath this problem, what you'll see is that it says the integral will diverge if either of the two integrals diverges. We've already determined that this first integral diverges, so at this point we can stop the problem and say, we're done, the integral diverges. But if you would like to, we could also look at the second integral and see what happens there. Well, we know secant of pi is going to be -1. The absolute value of that will just be 1 since it's inside the absolute value. And we know ln of 1 is going to be 0. Plus pi, and then minus the natural log of secant of b. Well, if b is approaching pi over 2 from the left, then secant of b is approaching -infinity. Again, since it's in the absolute value, we would then just say that's going to positive infinity. And again, ln of positive infinity is infinity. So again, we have an integral that diverges. Technically, we have minus infinity, so that part would go to -infinity. Okay, but again, now that we know that at least one of the integral diverges, since the first one diverges, we know the whole thing diverges. So we could simply just say that the integral diverges. One of the things you may have noticed are when an integral converges based on the power of x in the denominator. So some of these findings can be summarized in this box here called a special integral. It says that the integral from 1 to infinity of 1 over x to the p dx, that this will diverge if p is less than or equal to 1. If p is greater than 1, however, this will converge, and more specifically, we can find out what it converges to by using this formula. Let's go ahead and apply that formula to these two examples here. The first example has the integral from 1 to infinity of 1 over x squared dx. We can see from the above box that this will converge. What will it converge to? Well, rather than taking the integral and the time to find that out, we can simply use the formula in the box. So this is going to give us 1 divided by p, which in this case is 2, minus 1. So that would give us 1. That saved us a lot of time, but again, this rule only applies when you have something of this form. Let's look at that second example. The integral from 1 to infinity of 1 over x to the 4th dx. Again, this will also converge according to the box above, and we can find what the integral is without having to take the integral. We just need to substitute into our formula. 1 over p, our p in this case is 4, minus 1. That's going to give us 1/3.